thanks to all the organizers for organizing this conference and for this opportunity to present my work here. This is my outline slide. I will first provide the motivation for doing this automating the chirality detection, and then talk about the data set, how we train the model, and some of the results and conclusions that we find. The main motivation of the study was basically my previous study, which showed that filaments on the sun, which are the main sources of CMEs, can be used to get the direction of the magnetic field in the ICMEs or interplanetary CMEs near the Earth. And depending on what the magnetic field orientation of this ICME is, whether it is north or south, it will interact with the Earth's magnetic field to cause geomagnetic storms. So that can be determined by looking at filament magnetic field while it is on the sun. So the chiralities are right and left basically, and we use filaments in the study from H-alpha images and magnetogram images to get the polarities of the filaments to get the axial field direction. From the axial field direction, we mainly obtain the vertical component, which is the BZ of the filament. And then we compare that with the plasma parameters in situ in the solar wind, obtained using in situ satellites like ACE and WIND. We look for smooth rotation in total B and corresponding changes in due to expansion in speed and density and like other parameters. If we see that there is a CME or ICME structure in the solar wind, we then look for the BZ and the DST index to see what effect it had on the Earth's magnetic field. So we conducted the study for data between 2007 and 2017, and also for another run between 1996 and 2006, which are published in these papers. The results are also tabulated here in this confusion matrix. Out of the 83 filament ICME pairs, there are about 61 of them that showed that same configuration between the BZ of the filaments on the sun and ICME BZ. And in the 1996 to 2006 study, there were about 66 out of 102 filaments. That was about 65%. So overall, from 21 years of filament ICME pairs, we get about 75% match rate between the two BZs, BZ of the filament and BZ of the ICME, which means that 3 out of 4 CMEs retain their axial field direction while traversing through the interplanetary space. This gives a great precedence for filaments to be considered for space weather predictions and can be done while they are on the sun, so well ahead of time. So automating chirality detection. Because filaments can be successfully used for predictions, we think automating the process will make it even more robust. This can also be further integrated with already existing feature tracking tools such as HEK, and in time most other wavelengths can also be incorporated. This is basically just the first step in automating the usage of filaments for space weather predictions, the chirality detection. The next step would be to use magnetograms along with chirality determinations to get the axial field directions of the filaments, which will tell us whether they are north or south, and if they will affect the Earth's magnetic field or not. Okay. So our dataset mainly consists of H-alpha images of filaments obtained from Helio research given by Sarah Martin. The data are a small field of view with a 0.9 arcsecond resolution. This was my main motivation to use the data because compared to one arcsecond full disk images, because chirality is usually difficult to identify in low resolution images unless they are very high quality and big contain big features, big filaments. But the main problem with this data set is that it is from 2010 to 2018 observations, so just 8 years with mainly campaign observations, and is good for evolution type of studies rather than a variety of individual filaments. But we thought it would be good to use these images to see if models can learn different chiralities. So there are also prominences, sunspots, and prominences and sunspots in our dataset. So we are basically doing object detection for left chirality, right chirality, and prominences and sunspots. We also have ambiguous filaments, which they are basically filaments whose chirality could not be determined. So overall, we have 227 unique images, and they were labeled for these different classes using label box. We use YOLO V5 for training the model. YOLO V5 because it is a one-step neural network. It does both object detection and localization in one neural network, unlike some of the other popular ones. And it is also easily implemented using Python, and it is fast to train and run inferences. So the YOLO network is based on a deep convolutional neural network architecture that divides the input images into a grid of cells, with each cell responsible for predicting the objects whose centers fall within that cell. The network then uses a set of anchor boxes to predict the bounding box coordinates and class probabilities for each of the objects in the image. To detect the, yeah, okay. All right. We trained the model in 150 epochs in batch sizes of 16 using the default stochastic gradient descent optimizers from YOLO. And it uses leaky ReLU and sigmoid activation functions for activating the neurons. So because we have less number of data, we performed external flip functions and renamed the labels because flipping chirality will change the chirality to opposite chirality. So we need to rename them. And this way we obtained about 400 images in total, and further YOLO also takes care of for augmentations such as scaling, rotation, and translation, which can be given as inputs. While it is training the data. The results for the test set of the data shown here. The sunspots and prominences seem to be doing very well. The number of prominences in the test set was very few, about only 31. So this number seems to be low, but overall it does very well in detecting prominences. Left and right chirality, of course, we ideally want them to improve the precision and recall. We believe adding more data would improve the precision and recall because the features that determine the left or right chirality are very similar. So this means that it needs more examples to learn from. So basically, we plan to add more data and train this again in the near future. Here I show some of the inference results. On the left is the image with the ground truth bounding boxes. On the right are the predictions. In this case, it seems to have detected all the features well, but that is not always the case. So here we have left chirality, right chirality, right again, and some of the left features with the sunspot here, and it predicts the same on in the right shown here. Okay, in this case, it fails to detect some of the filament features like this big filament and one of these smaller filaments. In the case of prominences, it seems to be detecting all the prominences very well. Okay, so the main conclusions from this work is that chirality can be detected using machine learning algorithms, hence is feasible for automation. This was the first step in the process of doing space weather predictions using filaments and automating them. The next step would be to incorporate the respective magnetograms to get the actual field directions of the filaments. Obviously, we also need a lot more data to improve the results and get a better and more robust model. It will also be beneficial to incorporate data from different instruments. So thank you again for letting me have, for the organizers for letting me present, and also please contact me if you would if you have any questions or suggestions in how to improve these results, and also if you would like to collaborate or use my data and also give me some filament data. Thank you so much.